Yeah.
So there's an awful lot of like the golden learning how to surf. There's a lot of Cro-Magnon people that, well, let's see, they learned how to make tools. That's another step. So we have so many of these additions in us right now. The thing I see, the issue that I think is blocking people is that we live so high in the information processing thing that it's tough for us to understand how dogs work. It's tough for us to understand how slime mold works. I think there's an essential distributed nature where, slime mold, each cell takes care of itself first. And then it communicates with its neighbor. And what it learns is, oh, gee, there's a lot of me around. I'm going to bud. I'm going to do what's right for me. These are all, genetic hardware DNA algorithms it has. And this ability to add additional. Now, I think the cortex, for instance, the advent of the cortex is below the cortex. The nucleus have kind of a genetic purpose, and when you get to the cortex, suddenly, when you're born, you don't know what the purpose. When they're born, they don't know the purpose. Or just as they're born, they get their purpose. So you can learn to play the piano, or blind people have used their V1 areas for other things. There's a recasting of. Anyhow, I'm just going on.
That's fine.
Ask me a question.
So would you like to introduce yourself and what you do?
Yes.
Yeah, you're in there. I think we're finished. There's still some people talking. Yeah, but you can, I don't know. Yeah, it's up to you.
Yeah, we can stay here for a while.
Yes.
Good.
Thank you. Yeah. So.
So I'm Alan King. I started on this. I went to MIT in the late 60s, early 70s, and I had a number of professors like Marvin Minsky. Marvin said, everything the brain does is a mechanism. We don't know what the mechanism is yet, but that's your job. Go out and learn it. And also I had Jerry Lettvin. He had just published what the frog's brain tells what's the frog's eye tells the frog's brain. And so they kind of got me started on this. And for various other reasons, I went off into engineering. A hardware engineer, system engineer. I worked for Raytheon, BBN, Prime, a startup, a number of companies. And basically, I took what people wanted and reduced it to, first of all, functions, and then split the functions up into, this is the hardware part, this is the software part. So I've worked on some very, very large systems, like back in the mid-'80s, 100,000 processors in a shared memory environment, and how you do synchronization primitives on that. Or in 2000, I was part of a startup that actually made Avicii, that made the world's largest router, which had about 1,000 nodes connected by the fabric. I did the functional simulation, lightweight simulation of the fabric to determine how well it works. So I think in state machines. I kid people that I design finite state machines in my sleep, and that I've had dreams about them. But from my background in the 60s, 70s, I always had in the back of my mind, well, okay, how is what I'm working now for my job, how could that be in the brain? So I've had that, and I've had a chance to be independently financed for the last 10 years and been thinking heavily about it. Studied neurology quite a bit, and trying to put it all together. I'm in a space now where things seem to be coming together. It's still very high level. It's way above algorithms. I think that there's the possibility of driving it down. That's actually why one of the reasons I attended this conference was because there's a lot of lower level or detailed implementations. Although I have to say, recursive function theory and brains don't go in the same sentence for me. I think that when you look at human-animal intelligence, you really want to look at animal functions. You want to look at autonomous things, that communicate with their neighbors because it's better for them to communicate with their neighbors. Let's see. And I've been working, so I've come up with this architecture. This could actually be, as it said in the video, this could be the architecture document for a project, or the beginning of an architecture document.
What's the project called again?
What's that?
The project name?
Oh, I'm not that far along.
Okay.
You know, I have to find a sponsor first. I'd like that problem.
Okay, so you mentioned Marvin Minsky's Society of Minds, and you're thinking of building the architecture around that. Would you like to expound on this?
Well, I think this is an implementation of his basic idea. He talks about actors, and when he talks about actors, they look kind of me like software programs that can do kind of moderate-sized jobs. And I've taken a slightly different approach, which is to talk about a fractal. Now, a fractal is a play on words between a fact and a fractal, which has nothing to do with, but a fractal. And basically, each fractal represents one bit about the world. So I have a fractal for a camera. Right now, I can see a camera, so that fractal. You know, people have talked about the Bill Clinton cell. Interesting, Jerry Ledvin had Jerzy Konorski, who invented the grandmother cell, in one of his lectures. This was back in 69, or maybe it was 70. And the grandmother cell has been kind of discredited by science, but I find it a very simple, easy explanation of things. Of course, it's a distributed representation. There's not one cell. But if I say I have a camera cell, then I can actually use that as a shorthand for, well, in my recognition, I have these things. In my how I act in front of a camera, I have these other things. So it's distributed all around my cortex. But the concept of a grandmother cell has some value. And the value is that the brain is very, if you look at the brain wrong, it's very complicated. I think if you adopt a bunch of models, perhaps like the grandmother cell, fractals, and stuff I'll talk about are in the paper and I'll talk about tomorrow, that it kind of boils down to managing facts, desiring facts, remembering what predicts a fact, you know, and finding associations. So very early mechanisms had hardwired reactions. You know, the E. coli cell, if it's going closer to something, twiddles its thing forward and it goes closer. But if it goes away from the food, it twiddles its thing backward, which means it goes in a random direction, and then maybe it goes farther, but it does it again. Ultimately, it goes close. So that's a hardware reaction. That only works so far. And what I think the brain developed was the ability to say, food and, well, maybe that's a bad one because that's pretty, but, you know, I'm thinking of an example. You know, if I go to this bar, I can pick up a girl, but that's maybe not socially correct.
So the ability to model the world?
The ability to know what goes together, and also
instead of just a simple lock and key and, like, you know, trap jaw approach, sort of.
Like every E. coli is the same, so you can, and that has two advantages. One is that the wiring, the amount of information that has to go in the DNA expands drastically as you have a lot of channels, and it learns slowly. That's the first advantage, the first problem. The second problem is you've got a changing environment. You know, all of a sudden the ice age comes, and you have to learn ice means this. And I think all the learning that the cortex does is driven by a static evaluator in the amygdala, which then triggers basal ganglia kind of stuff saying that was good. If the amygdala says, yeah, you're in a good spot now, then all the things that got you there suddenly get marked plus, 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 plus. If on the other hand you're halfway over the edge of a cliff, those things that got you there get... So you have this mechanism for experiencing things, remembering whether they're good or bad, and then search algorithms. Basically, the basic search algorithm is I want to get over here because I have a desire, I have some need, and I must avoid the bad spots and go to the good spots. And it becomes a rather generic thing. Of course, defining the good spots, and that's the whole mechanism of learning. For instance, the amygdala, you can learn that certain things are good and bad. It's not a hardwired thing. It's kind of convolved because areas of the cortex actually affect how the amygdala analyzes things as you learn that some things are good or bad.
Right. So in designing a conscious machine, will it be self-improving? Do you think it will be able to improve on itself, reprogram?
I think you could build one that you wouldn't know whether it was silicon or nerves. In fact, the joke of the science fiction Battlestar Galactica, where there's the Cylons, is I think the Cylons are identical to people. The machines and the people, there's just no difference. It's just that one you have to plug into the wall or have a battery, and the other one you have to put food into. But you could build it. Now, whether you actually choose to do that, that's another thing. And there's issues about that. One of the interesting things I think is very interesting is you could build small machines that are kind of adjuncts to people. So you could build a machine of fractals that had some connection, and you could learn to, well, people already control a mouse with just brain waves. But it would allow much more like thinking something and having it happen, as opposed to saying something and having it happen. And learning, and the fractals would kind of learn. I'm not tremendously, I'm driven by the question of how does it work? Before I die, I want to know in my mind how the brain works. And I think there'll be a lot of practical applications, but it's just intoxicating to think about them now before you have something working.
That's right. When I interviewed another guy, John Smart, and he said he talks about the digital twins, which not only help you do things like move mice and operate in the world physically, but they can also have the tremendous power of data mining that computers have that we just cannot focus too much attention on. So you're in a supermarket, you're deciding which product to buy, you have a value system. It learns your value system in a way that it can help you choose a product that doesn't, choose a tuna that doesn't kill the dolphins, that doesn't come from the company that dumps stuff in the sea.
Right. And you can almost subconsciously access databases in a computer. Yeah. You know, what's the best price? You know, it'd be really neat to think that and have the answer come back.
Absolutely. I mean, all these sorts of things that we cannot really make informed decisions on now, we might be able to have augmented by having sort of like cognitive architectures in the outside world to help us sort of make these sorts of decisions.
Yeah.
So we have business intelligence, right, in the business world, don't we? But that sort of application, maybe not the way it's architected, but that sort of need may actually transfer not just to this business, but to the individual.
So there's a milestone that's before that, though. Yeah. What I'm in the process of doing is building a simulation environment where I can get a bunch of these fractals working, and you know, it may take 20, 50,000 of them together to play Super Mario Brothers. There's a lot about attentional mechanisms, a lot of higher mid-level stuff that are above the fractals. But once you do that, then you're going to see either I got a task like an assistant, and gee, I can build it in something that's about this big. Hey, you know, it'll fit in my iPhone. Great. Or you may say, yeah, I can have an assistant that I like, and it's about twice the size of this room. Okay? Now, that's a bad answer. But it may be that, you know, I don't know. So that's, once you get to that place, then you can kind of decide how you want to roll it out. This has kind of a little bit of the flavor of the Wright brothers flying. You know, they were worried about efficiencies of propellers and wing surfaces and low, simple control mechanisms by pulling on the wire. And they weren't particularly worried about whether you could charge for a fare across the Atlantic or something like that. That's downstream. So I'm really focused on getting something that actually had, and in the process of doing that, I have this division that you saw in the paper, but it's kind of the best guess I have at how to go all the way from humanness to mechanisms. But there's a lot of machine learning, AI, Solomonoff stuff that is going to come to bear. And my guess of the way to do it is to publicize it and get people thinking about it. I can't possibly do all that. That's, you know, but as such, this could be an organizing principle for work. Because if you have a straw man, something working, then a psychologist can say, well, I noticed that this ethical question was answered this way, and you got something that you can play with, and you can add it. You can add that information to how the maps of the Brodmann area, and I think real progress will start happening at that point.
Yeah. Oh, it's exciting time to be alive with this, especially.
Yeah.
Yeah. I have got some generic questions. Let me just ask if I can. Yeah. Let's have a quick browse. Here's this was meant for someone else. Was it? I don't know. Oh, that's probably. There's one. Have you ever heard of Steve O'Mahundra? I got some questions that I posed to him, which are pretty sort of generic and good.
You see, I have not had. I've kept current with the kind of what's been going on, but from a distance. So I don't have a lot of references, and I think that's the coming to a conference like this really helps that.
Oh yeah, definitely. Well, I'll ask you anyway. So, are you? Do you know what you know about strong AI? Don't you?
About what?
Strong AI is the term. It's like a not narrow but general.
Yeah, I know about true AI.
Yeah.
Yes.
Yeah. Well, how would you describe that?
Well, yeah. I think I use the term night science. So true AI is kind of the vision, what you want it to be. And then there's been neural nets, expert systems, which are things that DARPA would pay you money for. Okay? So I think that true AI is more about the vision. It's more about where you want to go. And to make something in the world, you have to make it real, each one of those things that happen. I hope that what I'm talking about, or some variant of it, turns into the next one, and it's more powerful.
So, how far away do you think we are from true AI?
Oh. Anywhere from 5 to 50 years.
Still, that's not all that long, really.
No.
I mean, like when you look at the philosophically, it's not that long.
Here's who is it? Future Shock Toffler talks about change accelerating, and I think that people like myself, I'm really the first generation that has grown up with computers as a thought model. Helmholtz, David talks about the reenactments into there. That's cool, but he never really thought it was possible to build. And when you think something's possible to build, you think about it differently. Another related thing is simulation. I've earned a fair amount of money simulating other people's ideas, lightweight simulators, like the routers and the multiprocessors. And I think about the fear of simulation. If I have this great idea, oh sheesh, I'm going to have to simulate that. What have I forgotten? and it brings a level of reality to it. And I think that people, since the computer has become so popular, people think more mechanistically than they did 100 years ago. They think deeper. So it could be 50. I put 50 on the outside, but that's past when I die, so...
Nice. Do you think consciousness is required to build a true AI or a general artificial intelligence?
I think consciousness is a red herring. I think that when we build an AI, we'll find out that consciousness has these 5 components to it. 2 that I can name off the top of my head are attentional mechanisms. My consciousness is here, or it's here, or it's here. The other is self-referentiality. I have an image of myself. Now, how that fits into the quantitative experience, I think we can only answer that when we have something working, and it may not even be a satisfactory answer. I just don't know. The one thing that one of the elements of my paper is the semantic network. And it always bothered me that the semantic network was just different in kind from all the other lower things. And then I realized that that is just a model that we have that describes it. And actually in the paper tomorrow, in the presentation tomorrow, I think there's a prediction mechanism that is, if you look at the implementation, there it is, it works. But if you want to understand how it works, well, semantic network is a good model of that. So it's a model in our head. And yeah, I don't know about consciousness.
Yep. Okay. Well, what about making AI, once it does reach a human level state, how do we keep it friendly? How do we keep it...
Well, I mean, the first piece of it is that there isn't much public awareness about the possibility of this. If I talk to a person on the street, they don't think it's possible, so they're not worried about it. I think that the other thing I think is that people who have had the vision that I have, or slightly different visions about, like the Cylons, for instance, can only profit from their work to live in the world by putting fear in it, because fear sells, and so that there's this, Frankenstein bias against machines. So those two things have to be worked. Consciousness raising, I'm not sure how to do it, but if people know how it's supposed to be, we get to choose what we want here. I mean, that's the bottom line. We can have it be horrible, or we can set up some ways where it can be wonderful or helpful. If I buy a conscious machine or a semi-conscious assistant, I'm paying the money for it. I want it to do what I want it to do. Okay? No, I don't want that brand. I want this brand. Okay? So there's that level of stuff. There's also, military killing machines, and they may be part of how our society evolves. You can't drive without a license, and you can't, they could be a positive part of the environment in the sense of having a society that's advanced. Certainly we saw the Aboriginal exhibits here, and the spiritual way of life of the people here in 300 or 400 years ago. And our civilization will be certainly much more advanced, if there's Aboriginal now and the future. Equal size steps.
Yeah, sometimes I get the feeling that we, in a lot of ways, technologically and scientifically, we're on a precipice. We haven't stopped developing. There's a common assumption that science has stopped, and that all the discoveries that are worth discovering have already been discovered. People think this, okay? But I see that, on a lot of fronts, I think we're almost tipping we're getting close to tipping points. I mean, 5, 50, 100 years, that's not a long time. Whether it's, now or in 100 or 50 years, it's not a huge time span when you think of the time span of human life on Earth.
Yeah,
or even civilized life.
To a certain extent, Tom Lehrer, the satirist of 30 years ago, says of Werner von Braun, he says, once the rockets go up, who cares where they come down? That's not my department. And I'm a little bit like that. I mean, I certainly have a conscience, but it's more about what's the efficiency of the propeller, how do you actually put it together and work? I'm definitely a hacker in terms of wanting to build as big a pile of stuff as possible. And the brain, I don't think there's a bigger problem.
Yeah, well, I mean, I think it'd be harder to simulate some of the complexities in the atmosphere of the Earth than it is to simulate the brain, but that's another point.
Oh, sure. I made that in a vague way, but yeah, possibly.
It's interesting, though, we did engineer steam engines before we had a theory of thermodynamics.
Yeah.
Interesting point. I remember that because I've got to say it during my talk. Is there any other points that you want to bring up that I haven't really thought of to ask? Okay, here's one. Is it important to think about the future of technology today?
I think it is, but if you spend more than 10% of your time doing it, you're not, at least for what I set my job to be, I'm not doing my job. There are so many red herrings around that people get trapped in. Since the room is empty, just between you and me, I think recursive function theory and information may have their place, but people can lose lifetimes in them. Actually, physical robotics is another case. I remember in probably 72, I went to Zilog, major computer manufacturer back then, and there was a bucket of chips. I dipped my hand in them, and I said, wow, imagine if you had all of these things working. I probably had 500 in my hand. And the first thing that came to mind was, well, people will do that. That's not a hard, that problem, and with multiprocessors, that's almost happened, the internet, etc. But the other thing is, what's the program you would write for it? And that's kind of where I came down on the Minsky, you just have to determine what the function is. One other piece to that. No, I'll get it later.
Is there any crossroads between scientific and technological development that you see as having a big impact in the not too distant future?
Ooh, what we're talking about here?
Obviously.
Yeah, I haven't thought much about things like that.
No, that's all right. Is there anything that you'd like to conclude on or say?
No, I mean, the thing that I'd like to conclude with is I think I'm putting together an engineering plan. And I think it's a big enough plan that a lot of people, there's a boatload of PhD theses in the stuff I'm talking about, dozens. And that's the way I'd like to see it go.
Nice. Well, thank you very much for your time.
You're quite welcome. Thank you for putting this together.
My pleasure. Excellent. All right.